Welcome to the next chapter on electrostatics. Electrostatics is the study of static electricity or charges. These charges originate in the atom. If you remember an atom, you will know that an atom has a compact center called the nucleus. The nucleus contains two types of particles: protons, which have a positive electric charge, and neutrons, which carry no electric charge. Small charged particles called electrons exist outside the nucleus. Electrons have a negative charge and are attracted to the positively charged protons. The electrons move in high-speed orbits around the nucleus, held close to the nucleus by the strong force of attraction from the protons. You can witness this force by rubbing rubber on fabric, creating an imbalance of protons and electrons. Small pieces of paper will be attracted to the negatively charged balloon. We call this static electricity because the charge don't move, it stays on the balloon. Two negatively charged balloons repel one another. The like charges on the balloons repel. This force can cause electrons to move from one place to another. When electrons flow between 2 points, we call that electricity. One of the most dramatic flow of charge is the lightning strike. Electrically charged clouds release their charge in an explosive flash. A powerful demonstration of charge flow. The space around a charged body where the force of attraction or repulsion is felt is called the electric field. Electric field is represented by lines along which the electrostatic forces act. These lines of force are called the electric field lines. The direction of an electric field at a point is the direction in which a positively charged particle would move if placed at that point. Usually, the electric lines of force are directed away from the positive charges and towards the negative charges. Like charges repel, and like charges attract. Keep in mind though that the electric field lines are always directed away from a positive charge and towards a negative charge. They do not cross one another. They are parallel at uniform field, widely spaced at weak fields, and closely arranged at strong fields. Charge distribution on the surface of a conductor. Charge distribution can be shown using spherical and pear-shaped conductors. The surfaces of conductors can be charged using generators, and the distribution investigated by touching the surface with a proof plane, which is a small metal disc with an insulating handle. The charge collected is then tested using an electroscope. For the spherical shape, the divergence of the leaf is the same for all parts. However, for the pear-shaped conductor, the divergence varies from one part to another, with the maximum at the point which is sharply curved. And the reason for this is because when the metal disc of the proof plane is placed on the surface of the conductor, it becomes part of that surface and acquires a charge which is proportional to the charge density on that section of the conductor. Sharp points have a higher charge concentration. Charge distribution for the spherical and pear-shaped conductors are indicated on your screen. Note, however, that the pear-shaped body discharges faster than the spherical shape because of the high charge concentration at the sharp curvature, which causes charge leakage. Charges on sharp points. From the foregoing, charge distribution on sharp points is extremely high. This can be demonstrated using a thin wire connected to a charge generator and placed close to a candle flame. It is observed that the flame is diverted as if there was wind emanating from the wire. This phenomenon is known as the electric wind. If the charge on the wire is positive, the high concentration of positive charges at the sharp point of the wire causes ionization of the surrounding air to produce electrons and positive ions. Electrons in air are attracted towards the positive conductor, while the heavy positive ions drift towards the flame, forming an electric wind. Lightning arrestor. Movements of clouds in the atmosphere produce large quantities of static charges due to friction with air. The static charges in the cloud induce large opposite charges on Earth, producing a high potential difference between the Earth and the cloud. The high potential difference makes air to become a charged conductor. The opposite charges strongly attract and neutralize each other, causing thunder and lightning. Lightning can cause destruction to buildings and any other objects standing on the Earth's surface. To save buildings from being stuck, a lightning arrestor is used. It comprises a thick copper wire with sharp spikes at the top. It is fixed vertically along the wall such that the spikes protrude above. The wire is then connected to a large thick copper plate buried very deep into the earth. The arrestor assumes the same nature of charges as the earth. Negative charges are attracted to the points and conducted to the earth. In case lightning occurs, the arrestor provides a path for the remaining charges to flow to the ground and thus protecting the building. Capacitors. A capacitor is a device used for storing charges. They are widely used in radio and television receivers and in transmitter circuits. The simplest capacitor is made by sandwiching a piece of paper in between two pieces of aluminum foil as shown here. This may not be a perfectly good capacitor in terms of its storage capacity, but it can store charges. When the terminals of a charged capacitor are connected to a piece of wire, sparks are produced, showing that the capacitor stores charges. Capacitors can hold enough charges to light a flashlight bulb for a minute or two. These are various types of capacitors. In circuit diagrams, a capacitor is represented by either of these symbols. In either symbols, the vertical lines, straight or curved, represent the conductors, and the horizontal lines represent wires connected to either conductor. Charging and discharging of a capacitor. A capacitor is charged by connecting the conductors to the terminals of a battery. Displayed here is a capacitor connected to a battery and an ammeter. To charge the capacitor, close the key. Observe that the ammeter is decreasing to 0. This indicates that the charges are flowing from the battery to the capacitor. Let us now understand what is going on. This is a diagrammatic representation of what we had. Notice that initially either plate of the capacitor had equal number of positive and negative charges. The plates are therefore neutral and the capacitor is said to be uncharged. When we complete the circuit, the battery will provide a driving force. Keep in mind that the positive charges do not flow. electrons will move from the negative terminal towards plate B of the capacitor. Consequently, the battery will draw electrons from plate A towards its positive terminal. The process will continue until plate A is completely positive and plate B is negatively charged. Notice the amount of charge increases with time. The charging is also fast at the beginning, but slows down with time as we near equilibrium between the battery and the capacitor. Thus, as charging continues, the rate of flow of electrons decreases, and thus current also decreases with time. When the capacitor is fully charged, no electrons flow and current becomes zero as well. That's why the ammeter indicated zero. To discharge the capacitor, you can either reverse the battery, which will reverse the charge flow, or simply remove the battery altogether and complete the circuit. The charges will redistribute and balance once again. You can also connect the capacitor to a bulb, in which case the capacitor will act like a battery and the bulb will light and glow dim as the capacitor discharges. Charge decreases with time. Electron flow is rapid at first but slows down as we near neutral point. Thus, current decreases with time. Capacitance. The capacitance of a capacitor is a measure of the amount of charge the capacitor can store when connected to a given voltage and is defined as the charge stored per unit voltage. Capacitance C is equal to Q over V, where Q is the charge in coulombs and V the voltage. The SI unit of capacitance is the farad F. 1 farad is the capacitance of a body if a charge of 1 coulomb raises its potential by 1 volt. Note that 1 farad is a very large unit of capacitance, and in practice, smaller units such as microfarads are used. Factors affecting the capacitance of a parallel plate capacitor. We have seen that a capacitor is made up of 2 parallel plates separated by an insulator called a dielectric. The distance of separation of the parallel plates, which is also the thickness of the dielectric, is marked as D. The capacitance is influenced by D and the surface area of the plates. It has been shown from experiment that capacitance is directly proportional to the surface area of the plate and inversely proportional to D. Capacitance also depends on the nature of the dielectric. Thus, C is proportional to A over D. So C is equal to epsilon A over D, where epsilon is a constant dependent on the medium between the plates and is called permeability of the insulating material. If the plates are in vacuum, the constant is denoted by epsilon naught, and its value is 8.85 times 10 to power negative 12 farad per meter. Therefore, C is equal to epsilon naught A over D. Finally, we look at capacitor circuits. Now, just like resistors, capacitors can be combined in series or parallel to provide an effective value. Let's look at capacitors in series. Now, on your screen is a set of capacitors arranged in series and connected to a voltage supply. When capacitors are arranged this way, there is an equal distribution of charge on the plates, and therefore Q1 is equal to Q2 and is equal to Q3. And the reason for this is because once the battery draws electrons from one of the plates, let's say capacitor 1, the negative charge on the negative plate of C1 induces a positive charge on one of the plates of capacitor 2. And this process is repeated until charges appear on all other capacitor plates. So let the charge on each capacitor be Q. The potential difference across the individual capacitors will be given by V1 is equal to Q over C1, V2 is equal to Q over C2, and similarly V3 is equal to Q over C3. But then V, the total voltage, is equal to the sum of the individual voltages. That's V is equal to V1 plus V2 plus V3. Substituting for V1, V2 and V3 in the above, V is equal to Q over C1 plus Q over C2 plus Q over C3, which gives us Q into 1 over C1 plus 1 over C2 plus 1 over C3. The only thing I did there is to factorize Q. Therefore, dividing both sides by Q, we shall have V over Q is equal to 1 over C1 plus 1 over C2 plus 1 over C3. But then V over Q is equal to 1 over C, where C is the combined capacitance. And therefore 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And that is the effective capacitance value for capacitors connected in series. Capacitors in parallel. Now in the parallel arrangement, all capacitors have the same potential difference across them. And this is clear as appears on your screen. Let the potential difference across them be equal to V, and Q1, Q2 and Q3 be the charge on each of the capacitors. Total charge Q is equal to Q1 plus Q2 plus Q3, but then Q1 is equal to C1 times V, Q2 is equal to C2 times V, and equally Q3 is equal to C3 times V. So therefore, Q is equal to C1 times V plus C2 times V plus C3 times V. Now if I factorize the right hand side, we shall have Q is equal to V into C1 plus C2 plus C3. Then I divide both sides by V, we shall have Q over V is equal to C1 plus C2 plus C3. But then Q over V is equal to C. And so substituting that, C is equal to C1 plus C2 plus C3, where C is the combined capacitance, and that is the effective capacitance for capacitors combined in parallel. Now, to find the effective capacitance of a series parallel arrangement, the network is systematically reduced into a single capacitor. Let's take an example. Now, the capacitors on your screen are connected in parallel and in series. Calculate the effective capacitance. Solution: the 2 microfarad and the 4 microfarad capacitors are in parallel. The combined capacitance is therefore equal to 2 plus 4, which is equal to 6 microfarads. The combined capacitors for the whole system now, we shall have the 6 microfarads is connected now in series with the 3 microfarads. and the effective capacitance C is equal to 6 times 3 over 6 plus 3, which gives us 2 microfarads. Finally, energy stored in a charged capacitor. When a capacitor is being charged, the addition of extra electrons to the negatively charged plates involves doing work against the repulsive forces of the electrons that are already there. Equally, the removal of electrons from the positively charged plates requires that work be done against the attractive forces of the positive charges on that plate. This work done is stored in the form of electrical potential energy. The energy may be converted to heat, light, or other forms. A plot of potential difference V against charge Q for a charging capacitor gives a straight line through the origin. The area of triangle OAB is equal to a half Q times V, but then QV is equal to work done in moving a charge Q through a potential difference of V volts. This is the energy stored in a charged capacitor. Work done, W, is equal to average charge times potential difference. That is equal to a half QV, which is equal to a half C times V squared, since Q is equal to CV. This is equal to Q squared over 2C, and the reason is because V is equal to Q over C. Note that the slope of the graph yields 1 over the capacitance. An example. A 2 microfarad capacitor is charged to a potential difference of 120 volts. Calculate the energy stored in it. Solution: work done is equal to the energy stored, and it's given by a half CV squared, which is equal to a half times 2 times 10 raised to power negative 6 times 120 squared. This gives us 1.44 times 10 to power negative 2 joules.
Time progressed into the mid-1800s, telegraphy has been discovered. Samuel Morse has devised the Morse code. They started with telephony, the telephone, sending voice across wires. By the 1890s, things really started to hot up. In those times, guys like William Crookes, various other experimenters, all started playing with this new phenomenon of high voltage using a device called a Ruhmkorff coil and passing this high voltage through tubes that the air had been exhausted from. So in other words, they had removed the air from these tubes and they tried to see what would happen if very high voltages were passed through this lot. Now, there is our cathode ray. You can see the ray appearing across the tube. This is the sort of thing that fascinated the scientists of those days. Now, this is very interesting because this led to all sorts of things. And of course, if you continue to experiment as they were doing, what would happen? Discoveries are bound to be made. And this, of course, led not only to the discovery of the electron, but also the discovery of something that I'm sure a lot of us have had dealings with in one way or another, the discovery of X-rays. X-rays were discovered by Willem Conrad Röntgen. He had photographic plates which were kept in a light-tight container so that daylight could not get to these plates. These were kept in a drawer. For some reason, Röntgen actually decided to develop these plates after having played with his cathode ray tubes. Now, remembering the light from the tubes had no way of getting to the photographic plates. Yet, when he developed the plates, they were exposed. There were markings on the plates that shouldn't have been there. he had then discovered what we today call X-rays.